So activities, whether they be research, social, or other, I don't know what else there is. And weekly reading groups, hikes, karaoke night. These are only a few ideas. We can come up with like things that were done in the past, but also, if you have specific ideas, it's a good time. Basically, that program is going to be what you shape it to be. So don't refrain. If you don't feel comfortable speaking on Thursday, please still attend. But you can also just send suggestions on Slack, and we'll take them into account. So I think that's all. I don't know if we're supposed to wait for a couple minutes. I think the trickle down of people has stopped. So we're gonna start the afternoon session. I'm really happy to introduce Sesh, who's gonna tell us about how to count subgraphs in sublinear time. So I'm not gonna take time away from him.
Okay. I will. Yeah. Is the mic working? It's good. Okay. So thank you to the organizers. Thank you to Ronit for inviting me to give this talk. This is work that I've loved and I love to share. Before I begin, I just want to pay tribute to teachers who have influenced my path, my undergraduate advisor, Manindra Agarwal, my graduate advisor, Bernard Chazelle, my surrogate advisor, Mike Sachs, and Tammy Colden, Ali Pinar, who mentored me at Sandia. And also thanks to my collaborators on this work, Talia Eden, who's one of the rising stars in sublinear algorithms, and Dana Ron, who is one of the giants in sublinear algorithms. And it's been my honor to work with them on these questions. So just at a high level, the basic question that we're looking at is how much of a graph needs to be seen for some approximate algorithmic task, right? And that's where the sublinear comes in. So, and also it's related to this question of how do you sample a large graph? So meaning there's some graph over here, and I've put this wizard as an oracle, and there's an algorithm that's asking questions and getting answers. And how many queries does it need to make, or how much of the graph does it need to see for some approximate algorithmic task? And again, based on Ronit's suggestions that this is meant to be a bootcamp talk accessible to everyone, I want to focus on some of the tools, and not so much on here's a litany of results. So my aim is to present some results in such a way that, how many of you are grad students? Very good. So as an exercise after this talk, I hope that you'll actually be able to go and work out the details yourself. Right? So I want to sort of show everything in full detail. And the question that we'll be studying is a pretty basic, simple question. I give you a simple undirected graph G, that's your input, and there's some fixed graph H. Approximate the H count in G. And the subgraphs to look at are as simple as just an edge. How many edges does your graph have? Or a triangle. How many triangles are there in a graph? But we can ask this question for more and more complex H. Just to be clear, we're not doing property testing here. This is actually just the algorithmic question, right? So the definitions are much easier. Yes, you had a question?
It count the number of times of the H's a subgraph of G or induced subgraph?
So in this case, it'll be both induced and non-induced because we'll be focusing on cliques. But in general, one could ask both those questions, and they're both equally interesting. I want to think about G being sparse, just to have sort of a mental model of what we're thinking about, but the results will hold in general. So they'll be parameterized by the number of edges and the number of vertices. So no assumptions on the graph. And we'll assume, as Arthur talked about in the morning, the graph is stored as an adjacency list, because that is the most reasonable representation when thinking about sparse graphs. Okay, so this is the question. We'll come to multiplicative, additive, and all of those things. But yes, multiplicative in general. And so now let me be a bit more precise. What is the model that we're accessing the graph is? And this becomes an important point, and I'll come to the end about a sticking point between applying these things in practice. So initially, let's assume that n, the number of vertices, is known. Let's assume that we don't know the set itself of vertices, we don't know the IDs. So nothing else is known. You just know the number of vertices in the graph. The way that you access the graph, and this is what is slightly abusing notation, is the standard sparse graph model as introduced by Goldreich and Ron. So the first is the vertex query. You can get a uniform at random vertex. So you press a button and you'll get a uniform random vertex in the graph. For any vertex, you can query the degree of that graph, of that vertex. So that's dv. For any vertex, you can get a uniform random neighbor. So this is called a neighbor query. And finally, if I give you, you can ask for any two edge vertices, which you have queried through some previous queries, you can check if that edge is present. This is called an edge query. Okay, so these are the 4 queries with which we access the graph. Again, uniform random vertices, you get the degrees, you get random neighbors, and you can query for an edge. Okay? And in some cases, there are some, so basically, algorithmically, it boils down to the algorithm can crawl, BFS, random walk from some starting random vertices. That's the power that the algorithm has. In some results, you can even get a uniform at random edge. So Sapir is nodding because he has worked on questions of that form. But I will talk about just the standard model without that, because I think that sort of highlights some of the basic techniques which are applicable in all settings. Okay, any questions about the model? Yes?
Regarding the last one, can you simulate the last one based on the other?
We will come to that. Good question. You could try to simulate. Yes?
In what settings does it matter that V is not known?
So like when you're talking to, when I'm talking to people who are, let's say, studying the internet graph, the IDs are often IP addresses, and they'll say, we don't know what IP addresses are out there. So they don't like this assumption that V is known. But on the other hand, maybe you could randomly sample through there's some method to do so. So I'm being somewhat pedantic about that. But I've heard people applied people really complain that you know what the list is explicitly. Okay, so the first tool is what I'll call heavy vertices. So, and hopefully in the next 10 minutes, I'll try to present a full-fledged result that the results, we'll be able to work out the details. So here's a very simple question. So as I said, the number of vertices is known, but the number of edges is not known. Let's estimate how many edges there are in a graph. Given that you know the number of vertices, this is equivalent to estimating the average degree of a graph, right? Because the sum of degrees is twice the number of edges. And so dv is the degree of vertex v, and d bar is 2m divided by n, the average degree. And this is what we want to estimate. Okay, this is the question. And let's start from maybe the most obvious procedure. Sample a bunch of uniform random vertices, query the degrees, take the average. Right? That's like the very first thing that you would think about. And it's a natural question to ask, how many samples do you need to get anything non-trivial? What can we prove about this very simple algorithm? And so what Feige showed in 2002, almost 2 decades ago, is that with square root n samples, you get a 2 approximation. And I'm going to prove that result to you. And this is, it's somewhat, so firstly, let's assume that the graph is connected. But we don't need to make that assumption in general. But that's just to give us some context. Because if there are isolated vertices, then I could take more than root n. Assume the graph is connected. So it's like saying that for 10 to the 8, which is 100 million vertices, you only need 10,000 samples, which I don't know. I think is kind of remarkable when you actually put numbers and you see that. Okay, so you might say, why a 2 approximation? Why square root n? So I'll show you simple lower bound examples that should convince you. So why 2? We'll consider a star graph. So that's just one vertex in the middle and n minus 1 vertices in the periphery. The average degree is approximately 2. It's like 2 minus 1 over n. But if you take little o of n samples, you're only going to hit the red vertices. You'll only hit the periphery. And so your empirical average is going to be 1. So you can't beat a 2 approximation even with sublinear, anything sublinear. Why root n? Well, let me take a graph which is a c root n clique and an n minus c root n cycle. To make it connected, I could put an edge between them. Now, what you see is that the average degree is dominated by the clique. The average degree is about c over 2, right? Because this clique will contribute like cn over 2 edges. But if you take anything significantly smaller than root n samples, you just hit the cycle. So the empirical average is 2. But the actual average is c. So which means that with less than root n samples, you cannot get any constant factor. Right? And so that explains the root n, that explains the 2. Any questions about these? Yeah.
Implicitly with the model you have.
This is, yes, this is this is actually for the simple problem. And with the adaptivity, we'll see that we can do more. Well, even with the adaptivity here, you'll get hosed. So, but there you could get an improvement. Yeah. So let me redescribe this problem over here in a sort of more statistical language. So it's just the same problem, the same roadblock, but I'm going to do it in terms of random variables, just to get some understanding that we can use to improve, to get an analysis. So I've just listed out all the vertices there and their degrees, d1, d2, d3, up to dn. Pick a random vertex, look at the degree. I'm going to call that random variable x1. x1 because it's the very first sample that you picked. So the expectation of x1 is d bar, the average degree. And if I chose k IID samples, and I took their sum, which I'm just going to call capital X, it's poor notation x1 to x, but bear with me. Then the average is going to be, the expectation is k times the average degree, right? Just linearity of expectation. Okay. What about the variance? Well, if I look at the variance of x1, it's basically like the average sum of squares of degrees, right? Minus some other term, but I'm just ignoring that. So that's the variance of one sample. What is the variance of k samples? Well, we know that the variance of a sum of independent random variables is the sum of variances. So using that, the variance of x is k times the variance of one sample, right? So if I do k samples, then I get k times the variance. Okay, so let's just plug in Chebyshev and see what is the value of k that we need to get some kind of concentration. Right, sort of the first obvious thing you do in a randomized algorithms course, you'll say, okay, what is the probability that x minus the expectation is more than epsilon times, like that you deviate more than epsilon times the expectation? Well, that's the variance of x divided by epsilon square expectation x squared. Right? I just wrote down Chebyshev. Now I'm just going to plug in these quantities over here because I can express the variance of x in terms of the variance of a single sample, which is x1. Okay, so that gives me k times the variance, and the denominator I'd get a k squared because I have the k times the expectation squared, so I just canceled it out for you. Okay, so I get this expression. Now, ignoring the epsilons, what this says is the number of samples I need is the variance divided by the expectation squared. Again, very standard sort of analysis that you'd see when you look at the Chebyshev inequality, right? Nothing fancy here. So I'm going to use this formula over and over again. Okay, so this number of samples I need is the variance divided by the expectation squared. And what we know is that if you plug in the actual setting here, the variance is like the sum of squares. So you get the sum of squares in the numerator, but the denominator, you're getting the average squared. Right? And the fact that there's a gap between this is exactly the problem that you saw on the last slide, just more mathematically expressed. More specifically, the numerator can be something like n squared. Like if there's one vertex of degree n, it's going to be n squared. But the denominator might just be n because the average is just 1. Right? So this is basically, in statistical language, just reframing the problem. Okay. Questions? Sorry, maybe I jumped in too quickly into this, but I thought, yeah. Exactly. Good. Somebody's awake. I'm doing my job. So, absolutely, right? It seems like you need n samples to get it, to estimate this random variable. So what we need to do is to somehow reduce the variance of the estimate, which is sort of obvious. And what we could do is somehow these high degree vertices are the problem. Could we just drop those outcomes? So if you learn nothing else, the word of the day to learn is Winsorize, which I was told by a statistician that this is called a Winsorized estimate. When you Winsorize an estimate, apparently you take a random variable and you drop it if it goes outside some bounds. So there's even a Wikipedia page on Winsorize. So anyway, so that's what we're going to do. And it seems like I'm just, I'm going to talk through this algorithm, then we'll have something concrete. So let me do the following thing, and this is the main tool, what I'll call heavy and light. Let me partition vertices into two buckets called light and heavy. Light vertices have a degree less than root m. Heavy vertices have a degree more than root m. Ignore the epsilons for now if that's bothering you. So root m is this is this threshold. Now, how many heavy vertices are there? At most root m, because the sum of degrees is basically m. So there are at most 2 root epsilon m heavy vertices. And the epsilons are bothering you, just ignore the epsilon. What this says is there are at most epsilon m heavy edges. Like within this, there are at most epsilon m edges, right? Because that's just the square of the number of vertices. Yeah? So what this means is that for every other edge, there's at least one endpoint on the light side. If the edge crosses, then it's only 1. But if the edge is completely internal, then it's 2. So what this says is if I look at the sum of degrees over here, I get at least 1 minus epsilon m. Because every edge that is not in this bucket is going to count once or maybe twice, but at least once. So what you get is the sum of all degrees is 2 times m. But the sum of all the light degrees is at least m over 2. And that's where your half is appearing. So the average degree of the light vertices is a half approximation of the average degree, half minus epsilon. Right? But the light degrees can't be too large. So I could go back, do Chebyshev, and I'm going to get some improvement there. And indeed, that's where you see the square root m appearing. So let's go ahead and do the math. Now let me define my random variable y1, which is one sample. It's just to say y1 is the degree of v if the degree is less than root m and is 0 otherwise. So this is this Windsorized estimate. I dropped all the heavy vertices. So what was the k that I need? I need the variance divided by the expectation squared. Now the variance I can bound by the expectation of yi squared, which I can just bound by the max times the expectation. Pretty simple standard bound. And let me plug that in over there. So the variance, I get the max times the expectation, cancels out with 1 of the expectation squared. So I get max divided by the expectation. Now what is the max value this can have? It's basically root m divided by the average degree, which I can also write as n divided by root m. Okay. So what this is saying is as long as m is at least n, root n samples suffice to estimate the average light degree. Yes?
Sorry if this is too early, but how can you actually do this algorithm if you don't know what m is?
You're way ahead.
Sorry.
You're ahead of the game. Good. More people are awake. Any other questions? Okay. So the average light degree is a half approximation and can be estimated with n divided by root m samples. The nice thing about this bound is it's a clean expression that deals with sparse, dense, all in one go. Like if m is n squared, then this is just constant. Right? So basically, yeah?
But if m is a small, like you seem to be assuming m is at least n.
Right.
Here and a couple of other places.
Yes.
Why do we make that assumption?
Well, the thing is, it's tight. It's optimal, right? Because if you had lots of isolated vertices, then there's no way you could beat that bound. So the only way that m is going to be less than n is you have isolated vertices. Or n over 2, let's say. Less than n over 2, you have isolated vertices. So assume the graph has no isolated vertices, and then m is going to be omega n. So the only bottleneck to all of these is the isolated vertices.
But is there some model that can handle these type of things actually? Because those are the ones that.
If it just distinguish one edge and no edges.
Yeah,
Need
so-
to query it all the.
No, I agree that the model itself was not allowed to work. with that.
You could assume, let's say you get uniform random access to a vertex of non-zero degree.
Yes.
If you did that, then all of this would clean up. Yeah. Okay, any questions about this? Okay, now it was correctly pointed out that how do you even sample y? You don't even know what m is. So the thing is, I'm going to use this as a trick in the analysis. I'm actually not going to sample y1. What I'm actually sampling is this variable x, which was n times the average of k degrees, which is basically my unbiased estimator. This y, which was n times the average of the Windsorized degrees, I know that its expectation is at least 1 minus epsilon m. It's not 2m. This is like the half approximation. I know that x is greater than equal to y. Is this clear? I want to understand what x is, but I have a tail bound on y. But this definitely works for one side of the tail. So the probability that x is too small is at most the probability that y is too small. I can apply Chebyshev on that. The probability that x is too large, just do Markov. The probability that it deviates more than 1 plus epsilon times its expectation is at most 1 minus epsilon. So I get weak concentration for the upper tail, but I get good concentration for the low tail.
You're using some epsilon somewhere.
Am I?
Y itself is 1 minus epsilon m.
So maybe it's like 1 minus 2 epsilon. Or... No, this is correct. This is legitimate.
Can you just guesstimate m and check?
In general, you can, but then you do have this problem that you might overestimate. Like, the thing is, if you're really unlucky and you hit some high degree vertices, then you might overestimate. So the thing is, you can do Markov. Feige gives a tighter bound than Markov on that. But essentially, the problem is it's really the lower tail that's an issue, that you underestimate. Because overestimating, again, is basically Markov. So what you can do is if you take a min of O of 1 over epsilon estimates, then you get concentration. And so in root n samples, you get a 2 approximation of the average degree. You can work out the details. It's not much left. It's basically, it's Chebyshev once you do this heavy and light partitioning. Right? That's the trick. Question?
Okay, so this is tight because the result you will get is tight, so you should not be able to improve it. But it feels like you're just bucketing in two things, and that seems kind of wasteful. Can't you bucket in more and get slightly better?
I mean, the root n is optimal. This is optimal. If you bucket more, you'll actually end up losing a log factor in the analysis. So it's tight, which is somewhat remarkable. That. Oh wait, the next thing I'm going to show you is even more remarkable. This is not even that interesting. Huh?
Tight for this axis module.
It's tight for this axis, but it's tight for a very natural algorithm, which is like querying a bunch of random vertices in a graph and taking the average degree. Right? So, okay. But what we also know is that, the root n is tight even if you were to do, yes, for this axis model. Okay. So far, so good. So that was the tool, right? Bucketing by light and heavy. And if you find the right way of bucketing, often you end up with the optimal answer for many of these questions. The second tool that I'm going to show you is called graph orientations. So again, let's estimate the average degree of a graph. But as was rightly pointed out, like the 2 approximation, it seems like you should be able to beat that. And so can you beat this obvious procedure that just samples a bunch of random vertices and takes the average? And what Goldreich and Ron showed is that you get a 1 plus epsilon approximation in root n time. Their algorithm, as defined, was pretty complicated. It did lots of bucketing and lots of careful estimates of various buckets. What I'm going to show you is, okay, maybe I'm boasting, but I think this is the book proof of this fact. And it is something that you could present in a lecture. So I'm going to give you an estimator. So here's the estimator. Pick a uniform random vertex U. Okay. Pick a uniform at random neighbor V. So just pick a random neighbor V. So you have U and V. Now query the degrees of these vertices. If du, which is the vertex you pick, du is less than dv, output 2 times du. If du is greater than dv, output 0. Break ties consistently. Like if the degrees were the same, then use the ID to break ties. But you have to do it consistently. Does the estimator make sense? And so pick a vertex, you pick a neighbor, query degrees, and you either output 2 times du or you output 0. Okay? So this is going to be my random variable y1 that I'm going to estimate, that I'm looking at. So to analyze it, let me describe this in a slightly different way. You can imagine orienting your graph into a DAG as follows. So I'll say u is less than v if the degree of u is less than the degree of v, or if the degrees were equal, then the tie breaking, basically put u lower. Right? So this orientation is just basically directing depending on the degree. And if the degrees are equal, then you're using the ID to break ties. Okay, so this orients the graph into a DAG. So dv is the degree, which is the thing that you query. dv plus is the out degree. Of course, you don't know what the algorithm doesn't know what the out degree is, but we'll use it in the analysis. Okay, so far, so good. Okay. So let's just sort of analyze the expectation of this random variable. So here's this vertex u. You queried this random vertex u. You're looking at the neighbors in green. And by the orientation, right, some of these edges are going to point inwards and some of these are pointing outwards. Again, we don't know the orientation, but implicitly the algorithm, when it looks at two vertices, can figure out the orientation by querying the degrees. Yeah? Okay, so now that we have this, what does this random variable actually do? It says that in the ones that are pointing inwards, you get a contribution of 0. And the ones that are pointing outwards, you get a contribution of 2 times du. Right? Okay. So what is the expectation of y1? So, okay, 1 over n, because I'm picking a vertex at random. Now, when I sample u, with probability du plus divided by du, I actually get something non-zero. With the remaining probability, I just get 0. So with probability du plus divided by du, I get 2 times du. Right? And so the du and du will cancel out. And so what I get is 1 over n times the sum of the out degrees. But the sum of out degrees is just m, because every edge is oriented one way or the other. And so this is an unbiased estimator for the degree. I was very happy when I saw this. Maybe you're not as happy, but I think it's pretty neat. So, and what I'm going to show you is that this estimator is going to have low variance. And then this gives you the 1 plus epsilon approximation. So yes, that was the punchline. We have an unbiased estimator for average degree. Question or no?
What does that give on the bad instances that you show? That's just.
What do you mean? So
Sorry.
yeah, okay. So what happens is in the star. So what you can imagine is that all the edges end up pointing inwards. So that central vertex actually has a contribution of 0. So the fact that you never see it doesn't bother you. So basically, the high degree vertices, their contribution basically goes down. And so the estimator ends up having low variance. Yeah.
Doing something like this split in the first algorithm, it's throwing away high degree vertices, sort of probabilistic.
Yes, exactly. So in that heavy and light picture, it's kind of pointing all the edges in one direction, so that this 2 factor that you got by different kinds of edges disappears. It's a bad way of putting it. Okay. So again, let's go back. So how many samples do we need? We need the max value of y1 divided by the expectation. Right? This is this thing that we've been. And what I'm going to show you is that this max is actually going to be small. Okay, so what we need to do is to analyze the max of this out degree. Okay, so let me just look at some vertex u, and it's pointing to all these vertices v. So what do we know? The degree, because this is pointing in this direction, the degree of v is at least the degree of u. That's what that pointing means. And the degree of u is at least the out degree of u, just because every edge is oriented one way or the other. So now let me just apply this bound. So the sum of all these vertices, their degrees, is at most 2 times m. Right? Because that's just, it's just the total sum of all degrees. And the green vertices are the ones that the u is pointing to. Each dv, as we said, is at least the out degree of u, du plus. And how many green vertices are there? Du plus. So it's at most du plus squared. Therefore, the max value of du plus is at most square root 2m. Okay, it's like another rabbit pulled from another hat. And so now when I apply this bound over here, what is the max divided by the expectation? Well, the max was square root 2m. The average is d. And again, I get the n over root m bound here. So here I can just apply Chebyshev directly. I don't even have to truncate the random variable or do anything. And so root n queries suffice to get a 1 plus epsilon approximation of the average degree. Okay, that's pretty neat. Again, it's something, and it's basically once you have the right tie breaking, it sort of all falls in place. Sorry.
In some sense, this algorithm is a graph algorithm. This one was not.
Yes. This is really a graph algorithm.
But random variables.
Yeah. But in some sense, there's some understanding from that algorithm that really helps guide this, because it's sort of obvious. Yeah, you start trying to understand how you're going to cut down the variance, and you want to reduce the effect of high degree vertices. Yeah. That's a good question. So I think that this bound in general should hold for hypergraphs, or I think maybe the 2 is replaced by the arity. Because it's every edge contributes that many times. I think it should also hold for a hypergraph of bounded arity. The orientation, so instead of orientation, you think of it as you have an ordering on the vertices, where you order the vertices by their degree. So I have to think about it a little bit, but I think it should be doable. It's a great question. Yeah. Yeah.
Is this degeneracy of the graph, or like orderosity, basically?
You're jumping 20 slides ahead. Yes. This root M is exactly the arboricity. And actually, the arboricity, you can actually get the arboricity in the bound here. Actually, it is the arboricity of the graph. So if this was actually a minor closed family, for example, then you get constant.
So then for hypergraph, is there a notion of degeneracy there?
It doesn't seem to have been defined, but I think there is value in defining it. So Daniel, my student here, have been thinking about subgraph counting questions where it seems like something like that might be useful.
Actually, there's a paper of me and a student where we did define some notion that we didn't seem to find in literature, but it was useful for precisely this counting generalizations of triangles and hypergraphs.
Okay, so I stand corrected. So it has been defined. Exactly this version, or?
Something that generalizes this, but yeah, it's not easy to describe, and I'm not sure that we have the right definition. We have something that gave us some results.
Okay, I'd be really interested in knowing more about that. So any questions? Okay, so I hope people are still awake, because the next one is a little more technically involved. But it's another very useful fact. So if nothing else, if you just learned this fact, I think it is useful for lots of subgraph counting questions. This is Chiba Nishizaki, an inequality of Chiba Nishizaki. So I'm going to now up my game. I'm going to do triangle counting. I want to approximate the number of triangles in the graph. And so we can get a 1 plus epsilon estimate to the triangle count in this somewhat funky looking time, like n divided by t to the 1/3, where t is the triangle count, plus m to the 3/2 divided by t. It's an annoying expression, but it's optimal. And what I'm going to show you are some of the techniques used to get that. And we'll be able to get sort of 1/2 of the result, again, hopefully in the next 15 minutes. So I'm actually going to assume access to uniform at random edges. So this is a result by Asadi, Kapralov, and Khanna, that in this model, they'll get a result here. The techniques that we had seem to be somewhat similar to what they did for this specific case, for triangles. So I'm assuming access to uniform at random edges, and then I'll show you how to get rid of it. So let me define my estimator now. So pick a uniform at random edge UV. Now we know that somehow this orientation seems to help us in cutting down the variance. So go ahead and do that orientation trick, which means we'll determine that U is the lower degree vertex of U and V, right? So you got this edge UV, look at the lower degree vertex, let's call it U. Pick a uniform at random neighbor W of U. So now you have this path of length 2, this wedge, and then just check if that's a triangle. Some random variable I've constructed. Right? And so let's also say that we want to estimate the average TE, where TE is the number of triangles on an edge E. And assume you know what M is, the number of edges, because you got that with the previous algorithm. And then you want to estimate the average number of triangles an edge participates in, and then you multiply that average by 3 times M, and you'll get your estimate. So you want to estimate this average TE. Okay. So, excuse me. So let me just define, I've defined this estimator here. Let me look at the success probability of it. So what is the success probability? So I sum over 1 over M, because I'm looking at summing over all the edges, or 1 over M. sum over all edges uv. Now, if I get an edge uv, the probability of success is TE, the number of triangles the edge participates in, divided by the min of du and dv. Right? Because I look at the number of sort of choices for step 2 is the min, and the number of successes in step 3 is the number of triangles. So this is the quantity that I get. This, I don't, it's not even clear how you would analyze this or use this to get an estimator. But let's start from here, which is sort of a natural place to begin. Now, what I'm going to do is I'm going to take this procedure, I'm going to tweak it a little bit, and use it to get an unbiased estimator out of this. And so sort of once you see this expression, you kind of start seeing the trick is somehow you have to multiply this by the min of du dv. If you could multiply it by min du dv, they'll cancel out, and then you end up with what you want. So what you say is check if it's a triangle. And if it's a triangle, then you output the min of du dv. Otherwise, output 0. So you, again, pick this edge, you orient the edge, pick a random neighbor, check if it's a triangle. If you land at a triangle, you output min of du dv. Otherwise, you output 0. And then now, you go through the work. The expectation is, so again, 1 over m, I'm averaging over all edges, sum over each edge. Is the probability that I succeed is as we discussed before, triangles divided by min du dv. But I get to multiply by min du dv because that's what I'm outputting. Lo and behold, these will cancel each other out, and then I end up with the average TE, average triangle per edge, right? So this random variable is unbiased. It has the right expectation. Yeah?
So far, it will also work if I do the max, for example, right?
So sorry, do?
If I do the max validation instead of the min, right?
Yeah, okay. Like you want to get the max of this.
Yeah.
Yes, that's going to be poorly behaved.
Okay. But
Good. Most of you are awake because you're jumping ahead a few slides. So let me go ahead and plug in the math again. Okay, so how many samples do I need? By this time, if I was a rock star, the crowd should say, yes, it's the max divided by the expectation, which is what you see. And so you want the max over all edges of the min of du dv divided by the expectation. And so you say, what is this expression? Maybe, maybe this thing is going to be small. And unfortunately, I can give you an example where this is really poorly behaved. So I could have this one edge, which has lots of common neighbors. Right? It actually participates in lots of triangles as well. But the min of du dv is actually n. So this max is going to be poorly behaved. But what I'm going to show you is, let's go back to this bound here, and I can get the variance to actually be much better behaved with a little bit of tweaking to this procedure, and that's where this Chiba-Nishizaki fact is going to appear. So what seems to come out of all of this is that the behavior of this min du dv, which is over each edge, look at the minimum degree of the endpoints, this is playing a role. And so Chiba-Nishizaki in 1985 have this inequality. Let's say that the sum over all edges of the min of du dv is at most n to the 3 halves. And the proof of this is it's pretty much what I showed you before with that orientation. And this is in the context of clique counting. For those of you who know what the arboricity or degeneracy is, this is the graph degeneracy. And so this bound is very useful in lots of triangle counting results. Triangle counting, clique counting results, like just knowing this bound, I have simplified, existing results. So what this says is the average of the min is root m. Unfortunately, the maximum value is extremely high. But let's go ahead and kind of do the analysis, assuming it behaves like the average, and then figure out a way of fixing this. The key tool you need is really this fact over here. So this analysis is, okay, I'm going to do it in 5 minutes, but it's much more at a higher level. Is there any questions at this point? You're right, you do care about the sum of squares for the variance. That is also seems to be ill-behaved. So we have a different way of dealing with it. So suppose this min of du dv was exactly root m. Just assume that was the case. Then let's go ahead and again just plug in our bound here. So we have k, the variance by the expectation squared, which is the max divided by the expectation. The max is root m. And the expectation over here, the expectation is exactly the average TE value. So if you plug that in over there, you get m to the 3/2 divided by t. So it at least starts telling you what is the expression you can hope for in the best case. This m to the 3/2 by t, where is it coming from? This is one way in which it's sort of naturally emerging by making, albeit a strong assumption. Okay? And so this sort of gives us the baseline of what we want to get. And now we need to deal with the case that maybe for some edges, this min du dv may be much larger. Okay, questions? Okay. Now, what I'm going to do is I'm going to do a trick to the estimator to reduce its variance even further. So here's what I'm going to do. So recall that my procedure was pick a uniform random edge, pick this uniform random W, check if that's a triangle, and if it's a triangle, output min du dv or 0. I'm going to actually repeat this procedure, min du dv divided by root m times. Okay, so where did I get this? I got like, but I'm going to repeat this procedure multiple times and then take the average. So if this min du dv is large, I'm going to repeat it more times and use it to cut down the variance. And if min du dv is less than root m, then I just need to do one repetition. But if it's more, I'm going to do more repetitions of it. So I'm doing something which is sort of edge specific. And I've done it exactly the number of times that the Chiba-Nishizaki will tell me if the running time works out. So how do I analyze? So the variance of the average is the average of the variance. So what I get is the variance of my estimator y1 overall. Okay, so let me do this a little carefully. It's the average variance of one of these zi's. So it's zi divided by the number of repetition. That's min du dv divided by root m. To analyze the zi, I just do max times the expectation. And the max of zi is min du dv. So I kind of plug this in. They cancel each other out. And if you didn't follow that bit, it's just a matter of like running the expressions. You'll get the variance of y1 is root m times the expectation. And essentially, again, when you plug this bound in, you'll get exactly what you want. Okay, so this might be a little hard to parse right now. The only important thing to know is that you repeat min du dv divided by root m times, and use it to cut down the variance. So when min du dv is less than root m, the variance was already low enough, as we saw. And when it's more, you repeat by exactly that many times to cut down the variance, applying this rule that the variance of the average is the average variance. Sorry? Good. So you're all jumping ahead. This is the next slide. K over here is the number of samples of this whole thing, but I now need to bound the running time. So the number of samples we need is m to the 3/2 over t, but the runtime per sample is not constant anymore. Or maybe it still is. So what is the runtime per sample? It's the average. So it's the average of 1 plus min du dv divided by root m. So I do the math here. The summation of min of du dv by Chiba-Nishizaki is basically m to the 3/2, and the root m over there and the m over there cancel it out, so it's at most 3.
Quick question.
Yeah?
But instead of the variance of the average, it should be the average variance divided by the number of things, right?
Yeah, you're right. It's the average variance divided by that. Yeah. I misspoke there, yeah. But the math was still correct. Yes. So the runtime per sample in expectation is still constant. Yeah?
Sorry, I'm repeating, but that's the expected runtime.
It's the expected runtime per sample. Yes. It's the expected runtime per sample. Sorry, yeah. So nitpicking is good because then I know that I haven't said anything that is wrong. Okay, so far so good. So the Chiba-Nishizaki inequality comes to save you right here. I mean, okay, so I don't know, maybe things are not magic, but it seems so magical. Like that root m that comes from that bound comes in over here, cancels exactly where you need it, and you get m to the 3/2 over t. for estimating the triangle count, assuming uniform random edges, and this is optimal. And this is pretty much all the details. Like, I mean, all you have to do is like now just plug in Chebyshev and see what you get. So I have about 15 minutes left. No, 13, because Clement said I have to end at 3. So I will not give you the full details on this, but I'll just show you one slide on the fourth tool, which is what I call like fake it till you make it, which is how do you simulate these uniform at random edges? So let me give you a procedure that's going to simulate uniform random edges using uniform at random vertices. You could sample some set of vertices R, query all the degrees in R, so line them up over here, and then set up a data structure that picks a vertex proportional to its degree amongst the set. Right? So D capital R is just the sum of degrees, and I sample U proportional, well, exactly equal to du divided by sum of degrees. So I could sample a random vertex from the set. Once I sample the random vertex, pick a random edge, uniform at random. So what this does is once I do this setting up, it gives me a uniform at random edge incident to this set in constant time or log n time, depending on your model. Right? So what I do is I'm basically just going to take a set of vertices, look at the incident edges amongst those, which I can sample, and use those as generic uniform at random edges. So I run the previous algorithm, which needs a uniform at random edge, using these edges. Yes?
So like this model, you only assume that you have access to like random vertices and then a random neighbor. Like those
Correct. And then you also need to be able to query the degrees. And to check for triangle closure, given 2 vertices, you have to be able to check if that's an edge. But all of those are essential, are like necessary for this. And so you use these as generic uniform at random edges. And okay, so here the analysis is much more complicated, but you can do some tricks that I'm going to skip over, and you can get this n over t to the 1/3 plus n to the 3/2. The n over t to the 1/3 is the number of vertices that you need to sample to be able to simulate that previous algorithm. This analysis is a little bit harder, and if you directly do it, you get a 3 approximation for the triangle count. You have to do some additional work to get a 1 plus epsilon approximation, but not that much more. Like, it's basically just using these tools in some combination or the other. And so, you know, in totality, there are these 4 techniques that I showed. Just want to go over them. The first was this thresholding of light and heavy, which you will see a lot in triangle counting work. There's some magic number that people will pull out and say, if it's less than this, do one analysis, more, do something else. And that is central to a lot of the techniques. This idea of graph orientations is very useful because it has actually simplified a lot of the work, which is comparing the degrees of vertices and to break ties. There's the Chiba-Nishizaki inequality, which is just the sum of min of du dv. This inequality and generalizations of it repeatedly appear in a lot of the clique counting literature. And finally, this trick of simulating edge samples by choosing a set of vertices and then using them. And by doing these techniques, you can prove, okay, so, I mean, if you're in the audience, I hope I cited you. I think I have. I'll just, you know, maybe a couple minutes show you some other results that are out there. So you can generalize a lot of the triangle counting to general clique counting. So it should be, sorry, this it's n divided by c to the 1 over k. But you get something that basically has k, where you're counting k cliques. You can also do it for k stars. So ignoring this complicated expression here, think of it as n to the 1 minus 1 over k plus 1, where you're counting k stars. So when k is 1, that's like counting edges. That's root n. But if you want to count the number of 2 stars, then it's n to the 2/3, so on and so forth. As I think it was Seperu pointed out, that there's this notion of graph degeneracy or arboricity, and that root m that you saw was actually the graph degeneracy, arboricity. And you can essentially you can replace all the occurrences of root m by this graph degeneracy. Now, ignoring what that actually is, all minor Flea family of graphs have bounded degeneracy. So you can do clique estimation any of those in just n divided by c time, where c is the clique count. It's quite nice. And you get k star estimation n to the 1 minus 1 over k. Yeah.
Random edge sample, do you get this for free just from the analysis you showed, or you have to do some work?
It's a good question.
Seems to be just that.
I don't know. I'm not sure. You mean like, can you
Just
just?
for triangles, for instance.
Yeah, I don't know off the top of my head whether you get it for free in that analysis. Maybe. Because I think we're just using the Chiba-Nishizaki bound. I don't think so, but we can talk about that later. There's also a lot of really nice work on actually sampling a uniform random edge or sampling a uniform random clique using these techniques. I'm going to sort of go quickly through some of these slides because there's something else I wanted to talk about. But I also mentioned, like, if you have access to uniform at random edges, there are a bunch of results that you get. And even though you may not have time to look at these, the slides are available, so at least the references are all there. I wanted to spend about 5 minutes on this question, though, because somebody had mentioned in some of the previous talks, and I think Ronit also called it. So, but is it really practical? To me, constants matter only when they don't. So the question is, what do you mean by practical? So one is, you can say the algorithms can be implemented off the shelf. That's one practical, which means that the constant factors are small. Maybe a more nuanced version is that these ideas can be used for faster algorithms. So we could use this to code up good sublinear algorithms. But a more nuanced version is, can you write papers in other conferences? Can you design algorithms that non-TCS people would actually care for? Maybe the most significant practical impact would be, can you solve algorithmic problems that other people actually care about? Who are these other people? I don't know. But maybe you write a SciPy package that people use. Like if you wrote k-means, everybody uses it. Or you make some money somehow. Right? So then it has practical value, at least for someone. So for the first one, I think the answer is no. You would not take the algorithm as described and implement it, because it's described to optimize a particular thing. Like we do lots of geometric search and all kinds of other techniques that are not that useful. Can the ideas be used for faster algorithms? I think that's a resounding yes. Like you can take these techniques, you can implement them, and you get good algorithms. Can you write papers in other conferences? Yes. I don't know. I mean, maybe. I wish. Let me show you some stuff, and then you can tell me. So one is, this is an interesting result by Talia Erin, Shweta Jain, who's in the audience, Ali Pinar, and Dana Ron, which is what we did is we estimated what's called the degree distribution of a graph, which a lot of people care for, which is like for a graph, how many vertices have a particular degree. So like this is saying there are at least these many vertices of degree 100, of degree 1000, so on and so forth. And how many samples do you actually need to estimate the degree distribution? So again, like what does this picture mean? Doesn't matter. The actual is red and ours is in blue and everything else is bad. The point is, a lot of people studied this problem and came up with complicated algorithms. We used the techniques that I discussed, and we were able to come up with a much better algorithm. And this was paper in www, not a theory paper. So, okay, so that checks one box, sort of. But the point is, there are questions regarding estimating average degree and estimating degree characteristics of vertices, which other people do care about. And we can solve those problems using these techniques. We did implement a sublinear triangle counting procedure based on those ideas. And there's some plot that I've shown. That plot is just saying that we work. It doesn't matter what it says. The quibble when I talked about a lot of these initial results to non-theory people is that they say, well, in the real world, you can't really sample uniform random vertices. And that was their biggest problem. Like the graph is unknown. Instead, what they will allow you is they'll say, you have some seed vertices, and you assume that the mixing time of the graph is small. Now, is that true or not? I don't know, but that seems to be a more palatable model that people are OK with. And so if you do that, you can kind of try to simulate some of these algorithms using a random walk. Like you use a random walk to generate random edges or random vertices, and then you use the basic techniques. And it does work then. And there has been some recent follow-up in actually applying these techniques just to get a general fast clique counter. Like that works in practice. Yeah? Exactly. So there are people who then studied that problem. And Omri is over here. He also has some results on like, how do you sample a uniform at random vertex, which seems harder than a uniform random edge. Yes?
Some algorithms in Laravel presented your way tight, but in some sense, right, these counterexample are maybe not realistic. So you could maybe ask like, for instance of demand.
I think so. I think it's a very valid question for many of those settings. And it seems like some of these algorithms work better in practice, like if you code them up properly. Like you have to be a little careful in like, you know, there are often lots of parameters that say, oh, make this min du dv divided by root m. But what do you actually do? In practice, you just plug in some number there. And so you have to tune those parameters somewhat. And this is exactly what was pointed out by like Dasgupta, Kumar, and Sarlor, Cherry Chetty et al., and then Omri, Ben Eliezer, Talia, Erin, Oren, and Fotakis had this question of how do you actually sample uniform random vertices given the graph. There's this big question of what is the right model. And I think a reasonable model that you could say is you don't get to sample uniform random vertices. So ignore the cartoons over here. But you start with a few random vertices, and the mixing time of the graph is small. That seems to be an assumption that people are OK with. And but I think there's a lot, you know, sort of, there's a lot of agreement or disagreement on what the best model is. I want to point out just something that I was talking to Tina Eliasirad, who's a very distinguished researcher in data mining. And she was saying that, somewhat quoting her, is that all applied researchers are really running sublinear graph algorithms because data collection is incomplete. So what she's saying is like, I'm basically collecting some sample of some data set, which is some snapshot of the ground truth. I'm running an algorithm on that. So with respect to the true ground truth, which is unknown, the algorithm is really a sublinear algorithm. And one of the questions she posed was like, if I run my favorite graph algorithm on some sample that I've computed, what does that say about the whole thing? Or how should I collect my graph data? This is a very difficult question to pin down because the sampling mechanism itself is imprecise. But I'll just throw out like two questions. Like an interesting sublinear question usually is people have a graph and there's some graph neural net or some machine learning model that outputs something. And if we were to say, oh, you can subsample this and still get similar outputs, I think people would be interested in that in the context of sublinear algorithms. Triangle counts by itself, maybe people aren't that gung-ho about, but I mean, I am, but you know, the rest of the world. It's 3 o'clock, so I'll just say that Talia, Dana, and I are working on a survey, so hopefully it will be out at some point. Thank you.
So I guess we have time for a couple of questions. So is there any question?
What is the query model that Tina and Eliasirad cares about?
The problem is I don't think she doesn't have, you know, they find it hard to articulate the model exactly. I think it's sort of like we have to give suggestions and then they will say that, well, this seems reasonable and this doesn't. So I talked to her a bit and we couldn't come up with something clearly. Because often people are just greedy. They will collect all the data they can, right? Without any sense of like, is this biased or not? So that's a very good question, though, yeah.
Yeah. Do we have any results? So real-world networks, they can also be multi-graphs, right? So do we have any results when the graph is a multi-graph?
It's a good question. No, we don't. I mean, I don't know if we have even any good theoretical questions that we can ask for that setting. But I think it's a very valid point to ask.
You said that like a query model there like other people are interested in is like they start from a few random seed nodes. Can you like, is it like truly random if they, or is it like usually?
So I can tell you what you need to write a paper, and then we can. What you could say is that your graph has low mixing time and you get access to an arbitrary vertex. But when people run experiments, they're often choosing those arbitrary vertices at random. So there's a big gap, even in the applied literature, between the model they say that they're solving and the one they're actually experimenting on, for what it's worth. But I think that, yes, assuming low mixing time and arbitrary, even maybe arbitrary random vertex to start with, is you could sell that.
If you have time, what was the exact question here? I didn't catch it. On that slide.
This one. Okay. So the exact question would be the following. So usually you have some machine learning model that takes as input a graph and outputs, let's say, a predictor. So it could be classification, like, is this of the nodes? And so is there some way in which, and so often these are set up in okay, so I have to be more precise in what I'm saying. So in some of these settings, so you have some training data that you're using to predict, and then the predictor actually has to work on objects it has not seen before. So imagine that the vertices are embedded in some space, and you're getting vectors which are not part of the training vertices. So can you subsample this part over here to train your model? It's ill-posed, I mean, but yeah. But I can throw you a more concrete one, if you don't mind. Like, get the cluster structure of a graph. Community structure, a cluster structure, without looking at the whole graph. That would be of interest to people.
So, okay, so if there's no more questions, and there's coffee beyond the doors, let's thank Seshadhri. We're going to resume at 3:30.